I was thinking to add the fish bowl inside. We already have the bowl itself. We just need to seal the edges so that water doesn't come out. Maybe replace the glass. It's a little foggy, but it would be a nice fish bowl, that's sure. Or turn it into a bird cage with parrots and such. Seal off the top so they wouldn't fly away. The mini mill that is still not working. At this point we've got issues with the saddle going back and forth on a rapid moves. That's how it started, and then it doesn't even move when it's doing the homing position. So you might have seen the earlier video where I was tackling the lubrication system. That is done. Looks like we got lube going everywhere. So this is the lead screw under. So right there is the lead screw under the saddle. And what I did is I did some inspection on the lead screw to see if there's any worn areas. You know, just touch it by hand and make sure there is no pitting or any other damage. So watch this. I'm gonna go and turn it over, and you can see a line of oil. Okay, you see a line of oil bubbles right there along the bottom line as the oil accumulates on the bottom. So that means that the oil that comes in, it will get to the lead screw nut. It will be distributed to the lead screw itself, because that oil is pooling on the bottom of the lead screw. So when I turn the shaft, when I turn the lead screw, I don't feel any, you know, it's smooth. I don't feel any kind of pitting on the lead screw. Turn on the machine and the lube pump and exercise the carriage back and forth a couple times. You can see I took off the wipers. There are the wipers. There's the other one from this side, and you can see there's oil on the ways everywhere on both sides. It's actually pooling here on this side. So oil is getting where oil is supposed to go. And now I took apart the Y motor, the servo motor for the Y stage, for the saddle, and I'm trying to troubleshoot the motor. So follow me on this journey. Welcome back to the shrine of the hand-me-downs of the industry, where nothing seems to be working these days. Seems like I've been here before. Variac, bridge, motor, voltage, speed, current, voltage. So let's see if she runs. She's a runner. So let's go up to 59 volts. 59 volts is the nominal voltage for 1000 RPM. Okay, so 59 volts, something around 59 volts. The PID control attached to my hand is trying its best. So 59 volts, running 1038 RPMs, so that's good. And then the tach is giving around 9.5 volts. You can see 9.9 volts, so that also checks out. And it is drawing 0.2 amps AC. So there's no high current draw. The motor is running. The tach signal is good. It's handy to have a lathe at your disposal for cases like this when you're trying to troubleshoot a servo motor from your CNC. So all we got here, gobbled up as you can see, the servo motor in its entire beauty. I got the encoder attached. The motor is chucked into the lathe. So when the motor shaft is spinning, it's driving this chuck. This is the 3-jaw chuck. I got a 4-jaw chuck, which would represent a lot more inertia, but I was gonna roll with the 3-jaw chuck. And I've got a target here on the chuck, a little magnet. This pickup is sending feedback here, so that is gonna show the speed with which the chuck is spinning. I've got a voltage meter here measuring the DC voltage that goes into the motor. I got a current meter that's measuring the AC current that goes into the bridge that feeds the motor. And all we need to do is just flip this switch and then give it some juice. So as you can see, it will start spinning the chuck. We are running 14 volts and it's drawing about 4.3 amps and it's running 110 RPM. So let's crank it up a little bit. I'm gonna go up to about 7 or 8 amps. This motor is intermittent duty, which means it's not working the entire time. Okay, so it works a little bit, then it has time to cool down. So we are running 7.5 amps at 28 volts and it's spinning the chuck at 241 RPM. So as you can see, the motor is running fine, and the previous test that we've done was at free speed, basically no load, but this is definitely supplying a specific load. I don't have any of the auxiliaries running on the lathe, so you can see the lead screw or the feed rod are not turning, so it's only spinning the chuck and the gears and the main prop shaft in the lathe. But again, the current is 7.2 amps, it's 28 volts, and it's spinning at 256 RPM. So I'm gonna stop that test because I don't want to overheat the motor. So as you might remember from one of the previous teardowns, the DC voltage that goes into the brushes, and then those brushes feed it into the armature. So that is spinning the armature. We have permanent magnets in this motor. So when we feed this 7 amps through the motor, it is gonna heat up the armature. And the only way that heat can go is into the thermal mass, so it's heating up the armature over time, and the air inside. So if the armature is spinning, it's churning the air, and then some of that hot air is touching the housing from the inside. There's conduction through the housing, and then it's dissipated into the environment. So that's why it's important, you know, to have the motor spinning, because they use these motors as a brake. I think they use AC current and they use it as a brake so that the table does not move when it's not supposed to move. And I think that is what's burning these motors up. You know, if the CNC is turned on for a prolonged amount of time without movement. Encoder is running. I use a little shady pole motor for my shady business. As you can see, it's turning clockwise this way, viewing from the motor end, and it's turning counterclockwise, viewing from the back of the encoder. Here's the specification. It says CCW viewing encoder top. So I am assuming this is the top of the encoder and this is the bottom. It's kind of shady the way it's put down on the paper right there. As far as the signals go, we got all 3 signals. You can see top is channel A, the blue second one is channel B, and then the bottom one is purple. That's the index channel, and you can see it lines up with the specification. So encoder is checked, it's working. Made a new tool, nice little spinner. We can use it to drive the table back and forth. At level 10, the drill can move the table in both directions. I was going to make sure that it ramps up slowly. So it's moving out. And it's moving in. And what we're going to do, try to spin the chuck with this drill. And you can see the size of the drill doesn't even compare to the servo motor. So what we're going to do is speed 1, and then we're going to do maximum torque capacity. Okay. So let's see what happens. So as you can see, even at maximum, the ratchet inside is gonna disengage. And I'm trying to spin it up as gingerly as I can. So it's spinning at 90 RPM. So it can spin up the big chuck, but it's only spinning it at 90 RPM. What we got so far, the servo motor will not home, and you can see the motor will run at free speed with basically nominal parameters. The motor will run under load, and in the same time it will consume 7 amps at 28 volts, and the motor shaft is going to spin at 250 RPM. I did some arithmetics, and 7 amps at 28 volts will be 196 watts, and 250 RPM is around 26 radians per second. So the torque is going to be power divided by the angular velocity, basically. So it comes out around 7.5 Newton meters. So when the motor runs at 250 RPM and delivers 7.5 Newton meters, it's right on the performance curve of the motor. The next thing is the encoder is working and has a good signal. The ways are clear and they have proper lubrication. The lead screw is not binding, and also the lead screw has good lubrication. I also checked that the hand drill is going to be able to turn the lead screw at high speed setting, you know, about 10 torque setting. The hand drill will only turn the chuck on the lathe at 90 RPM. So the hand drill is a lot weaker motor than the servo motor. You know, the servo motor turns the chuck at 250, the hand drill only turns it at 90, and the hand drill is able to move the lead screw. So there's enough torque available in the servo motor to drive the lead screw and move the saddle. What it all comes down to is the electronics. So the motor is good, the feedback system is good, and there's no binding, so it must be the electronics. What I did is, you can see when I turn on the servos, they come alive. There is no error message. As far as on the servos, there's a plethora of LEDs. There's no LEDs lit other than, you know, the green light on the servos. This is the servo amplifier, servo amp. It's made by Enelam. This company went under basically in the mid-2000s, and then someone bought them and they supported it for another 10 years, but there's no support anymore. You can still buy used equipment on eBay. I wanted to see if there's any apparent problems with the board. This is the heatsink. So you can see this is the base plate. It's made out of a 1/8 thick aluminum sheet. And so this is the servo board. As you can see, they all identical. What I ended up doing is I swapped the X and a Y, and I was monitoring it during the homing sequence, and the Y axis was moving back and forth normally. So it must be the servo board. This is basically the servo board. So we have two connections here for the DC, plus and minus, and then we have the motor connections, and then we have some low voltage connections here for the tech and some of the signal that comes from the computer. And then these are the LEDs that basically just response function to the user. So the green, when the green is lit, it just shows that it's turned on and everything is good. I tried to buy one on eBay and it didn't get here yet, so my hope is that once it gets here I will just flip these dip switches into the same position. I didn't wiggle them to see if they are loose like the other dip switch, but that's the plan. And there's no apparent problem with this one, so at this point I'm getting another one, and that's my best bet. So thanks for hanging out with me in the shrine. Hope you guys enjoy the video, and don't forget to hit that like button and come back next time. See you. Bye.